The water MO diagram requires first and second order treatment. We have looked at one example of a molecule which required first and second order treatment before the B2 molecule. In that case, the first order mixed to make the bonds, and the second order carried out the sp hybridization. In the case of water, the first order will do these things in the opposite order. We'll do the sp hybridization. And the second order will mix to make bonds. And at this level, you won't be required to know which is the right order to do, what to do in the first order step and the second order step. If I give you a problem in the final which asks you to make an MO diagram with first and second order mixing, I'll tell you which I want to be done first. If I want sp hybridization to be done first, or if I want to mix to make the bonds first. Okay, so let's go ahead and then straight to doing the first order diagram for water. Here it is. Here's we start off with the p orbitals on the oxygen, and they are all at the same energy, minus 15 EVs. Quite far beneath it, at minus 32 EVs, is the oxygen s orbital. But notice that the delta energy of S and P is equal to 17 EVs. 32 minus 15 is 17 EVs. 17 EVs is still enough that there is a small amount of mixing possible between them. Okay, and then on the other side we have the hydrogen, which is at minus 14 EVs. And I would always give you the energies on an exam of the various atomic orbitals. Oops, I shouldn't do it like that. When I mix them, remember, these are peripheral hydrogens. They are molecular geometry equivalent, and we always add and subtract molecular geometry equivalent peripheral atom orbitals. So we're going to have the addition and the subtraction. They are too far apart to make any real bond, but I guess one of them is infinitesimally higher in energy than the other due to the small amount of destructive interference. So they are at minus 14 EVs. And as I advertised, we are going to make sp hybridization first. But we cannot make this sp hybridization blindly. We have to have an eye to the variational principle, which is what is the lowest energy orbital that we can imagine. And if we are going to make sp hybridization, the orbital which has the greatest constructive interference will be this one, because we've maximized on both sides the amount of constructive interference, the most that they're pointed directly towards each other. So that's the orbital we want to make, and we're going to have to make it from these two. And so I'm going to mix these two, and here's what I'm going to do to make our life a little easier. I'm going to turn this one into, I'm going to turn this one into a different color so that we can see it. Okay, so what we're going to do is we're going to mix these two, and when we mix to hybridize this orbital with this orbital on top, we are not making a bond because they are orbitals on the same atom. We are averaging the energies. So this one's going to go up in energy a bit. This one's going to go down. This is going to be a mainly s orbital. And this one will be a mainly p orbital. And we're actually doing this hybridization because photoelectron spectroscopy is so accurate, we can actually detect the sp hybridization in its energies. And so that's why we need to do it in the diagram. Okay, so we're going to make psi 1 here. So let's see what psi 1 looks like. Put it over here. Here is phi 1. And here is phi 2. I'm just redrawing it. And so when I draw those two together, in the bottom region, they are in phase. So it's big. And in the top region, they are out of phase. So it is small. And so this orbital is going to be mainly an s orbital, but we draw it like this. That is psi 1. And then we must make psi 2. For psi 2, we need phi 2. I'll draw phi 2 in a different color here. I'll use this color here. This is phi minus phi 2. So this is minus phi 2. And to make psi 2, we need to take phi 1 again, and now we add to it phi minus phi 2, which I have in magenta, which is shaded like this. And in the top region, it is in phase. So it's big. And in the bottom region, it's out of phase. And so it's small. There I brought it like that. And remember, I'm averaging the two so they get closer together. And this is actually the only mixing we do in the first order diagram. We're only doing sp hybridization. So we carry over the remaining orbitals. I'll do them in black. We have these two orbitals. They are unchanged in energy. And we have these two orbitals unchanged in energy. We have 1, 2, 3, 4, 5, 6. 6 orbitals. We started off with 6. These 6 orbitals constitute the first order H2O orbital diagram. It's not an MO diagram. The second order is, and I'll do the second order diagram in the next clip.